In example 30.1, we're going to calculate the mutual inductance between two coaxial solenoids. The first solenoid is a long one which has a length L, a cross-sectional area, and a total number of turns N1. The outer solenoid has a total number of turns N2, and we're not given its length. So the two equations we'll need for this problem are the magnetic field of a long solenoid, where N is the number of turns per unit length of the solenoid, and I would be the current that's flowing through the solenoid. The mutual inductance between these two solenoids can be viewed from two different perspectives. The first is if I drive a current through the long solenoid, I can produce a magnetic field that produces a flux through the second solenoid. Likewise, I can drive a current through the second solenoid, which is going to produce a magnetic flux through the first solenoid. So we're actually going to take this portion of the expression for the mutual inductance because it involves the magnetic field produced by the long solenoid, and we actually have an equation for that as given here. So our perspective now is we're going to drive a current I1 through the solenoid. It's going to produce an internal magnetic field given by this value, which in turn produces a magnetic flux through the outer solenoid. The magnetic field that's produced is given by this expression, where we're going to replace lowercase n1 by the total number of turns divided by the length of that solenoid. The flux through the solenoid is simply, or the flux through one loop of this solenoid is this magnetic field times the cross-sectional area of N1. The reason we use the cross-sectional area of the long solenoid is that there's no magnetic field in between the two solenoids, because the magnetic field in the region outside the long solenoid is equal to 0. So here's the magnetic field of the long solenoid times its area, which is also the flux through one turn of the outer solenoid. But I have N2 turns, so I have to multiply by an N2, and I have to divide by the current flowing through the long solenoid. And here's my final expression for the mutual inductance. Notice that it doesn't involve current. In fact, all of the factors in here, except for the universal constant mu naught, are simply geometrical factors. And in fact, the mutual inductance is proportional to the product of the number of turns in the two solenoids, and inversely proportional to the length of the long solenoid. And this ends example 30. In example 30.4, we're going to calculate the self-induced EMF in a toroidal solenoid that has a current that increases uniformly from 0 to 6 amps in 3 microseconds. So the induced EMF is given by equation 30.7 and is simply equal to minus the inductance of the solenoid times the time derivative of the current. So for the solenoid of the previous example, 30.3, we calculated the inductance for the case where N was equal to 200, the cross-sectional area was equal to 5 centimeters squared, and the radius was 0.1 meters. And for these parameters, we found an inductance of 40 microhenries. The di dt in this problem is simply 6 amps divided by 3 microseconds, which is 2 times 10 to the 6 amps per second. Plugging into this equation for the self-inductance and just taking the absolute values, because we're not worried about the direction yet, we just want the magnitude, we multiply the inductance, which is 40 microhenries, times 2 times 10 to the 6 amps, and we get 80 volts. Now if I look at where the current's flowing into the solenoid and flowing out, if I call this point A and this point B, then by Lenz's law, the induced EMF is such to oppose the change in flux through each of these windings. And to do so, the voltage at B has to be greater than A. In other words, the induced EMF would choose the current to flow the other way. And this ends example 30.4. In example 30.5, we're going to explore the possibility of using an inductor as an energy storage device for the electric power industry. In particular, we want to calculate the inductance that would be needed to store 1 kilowatt hour of energy in a coil that's carrying 200 amps of current. So the potential energy of the inductor is given by this equation, equation 30.9, which states that the potential energy is 1/2 times the inductance times the current squared through the inductor. And our target variable in this problem is in fact the inductance. So the first thing we're going to do is calculate how many joules of energy are in 1 kilowatt hour. And that's going to be 1,000 watts times 3,600 seconds, which is quite a large amount of energy. Is 3.6 times 10 to the 6 joules. Rearranging this equation and solving for L, we find that we need an inductance of about 180 henries. This inductance can be compared to that of the previous two examples where we looked at the toroidal solenoid of reasonable dimensions, and we found that the inductance there was something like 40 microhenries. That means that this inductance is in fact about 5 million times bigger than this one. An inductor of 180 henries is in fact impractical. Such a device would be the size of a room. And this ends example 30.5. In example 30.7, we're going to examine the time dependence of the energy in an RL circuit. When the current in an RL circuit is decaying, we want to calculate what fraction of the original energy is left in the inductor after 2.3 time constants has elapsed. To answer this question, we'll need equation 30.18, which gives us the time dependence of the current through the inductor for decay. And you notice that R over L is 1 over the time constant. The energy in the inductor is given by equation 30.9 and is 1/2 L times I squared, where I now is going to be a function of time. So we're ready to begin. The current is given by this, again, and what we're going to do is plug this expression into the expression for the potential energy of the inductor. So we have this, and replacing I by this equation, we get this for the energy as a function of time. We're going to let U naught be equal to 1/2 L I naught squared, so this is the initial energy of the inductor. And at t equal to 2.3 times tau, which is 2.3 times L over R, we have an energy that's actually about 1% of what we started with. So if we return to the previous example, for that RL circuit, the time constant was about 400 microseconds. So to turn that circuit off and then turn it back on, in other words to completely cycle it, we'll require about 2 of these, or 2.3 of them, to get down to 1%, and 2.3 of these to turn it back on. So roughly speaking, it'll take about 2 milliseconds to cycle the circuit. And this ends example 30.7. In example 30.8, we're going to consider an oscillating LC circuit. A 300 volt DC power supply is used to charge a 25 microfarad capacitor. After this capacitor is fully charged, it's removed from the power supply and connected across a 10 millihenry inductor, and then it begins to oscillate. We're going to consider the resistance of the circuit to be negligible. And in part A, we're going to find the frequency and period of oscillation of the circuit. In part B, we're going to find the charge on the capacitor and the current in the circuit 1.2 milliseconds after the inductor and capacitor are connected together. So the equations we'll need for this are shown as follows. We'll need the angular frequency of the oscillator, and that's going to be given by equation 30.22, where L is the inductance and C is the capacitance. The charge as a function of time is given by equation 30.21, so it oscillates as the cosine of omega t, where phi is called the phase angle, and phi determines the amount of charge at t equals 0. The current is given by equation 30.23. In our particular case, the capacitor is fully charged at t equals 0, and so if I put 0 here, I need the cosine function to be 1, so I need phi to be 0. And we'll come back to this in a minute. So here's a diagram of the system where I have the capacitor and the inductor, and here's the switch that's closed at t equals 0. Starting with part A, the angular frequency is 1 over the square root of LC, which is going to be 2 times 10 to the 3 radians per second. The frequency in hertz is omega over 2 pi, which is 320 hertz, and the period is 1 over the frequency, which is 3.1 milliseconds. Now we want to look for the charge and the current at 1.2 milliseconds, which is about equal to 0.38 times the period of the oscillation. But recall, at 1/4 of the period, the capacitor is completely discharged and all the energy stored in the inductor is current. At 1/2 the period, the capacitor is now charged in the opposite polarity, and the current through the inductor is 0. So we're in between these two limits. And since we're in between, we know that a negative charge is beginning to build up on the capacitor and that the current has actually changed sign. So we need a minus sign on both those answers. So for the charge, we have this expression again, and our charge that we start out with is simply the capacitance times the EMF that was placed across the capacitor, which is 7.5 times 10 to the minus 3 coulombs. And again, phi is equal to 0 in this equation. So putting in the numbers, for t equal 1.2 times 10 to the minus 3 seconds, and omega t is going to be 2.4 radians, and Q is going to be minus 5.5 times 10 to the minus 3 coulombs. Doing the same for the current, putting in the numbers, we get minus 10 amps. And as expected, this charge and this current are negative. And this ends example 30.8. In example 30.9, we're going to examine the energy in the oscillating LC circuit. In particular, we're going to consider the LC circuit of the previous example, 30.8, and we're going to find the magnetic and electrical energies at t equals 0 and t equal 1.2 milliseconds respectively. The energy of the inductor is simply 1/2 Li squared, and the energy of the capacitor in the circuit is simply Q squared over 2C, where of course Q and I are oscillating sinusoidally in time in the circuit. So we're ready to begin. In the previous example, the capacitor was initially charged with an EMF source and then tied across the inductor. So the initial current in the circuit is 0 and the charge is at its maximum value. So the energy of the inductor is 0, and we put in the charge that we found in that problem, and we get 1.1 joules for the energy of the capacitor. At 1.2 milliseconds, we have a current of minus 10 amps from the previous example and a charge of minus 5.5 times 10 to the minus 3 coulombs. So these values can be plugged into these two equations, as I'm doing here, and we get the energy of the inductor to be 0.5 joules and the energy of the capacitor is 0.6 joules. The first thing I notice here is that 0.6 plus 0.5 joules is equal to 1.1 joules, and so the total energy of the circuit at 1.2 milliseconds is the same as it was at t equals 0. And this has to be true because there's no resistor in the circuit, so there's no dissipation, and hence there's no way for energy to get out of the circuit. I also noticed that from the previous example, 1.2 milliseconds was about halfway between t over 4 and t over 2, where t is the period of oscillation. So we're halfway between the capacitor being fully charged and the inductor having a maximum current. Not quite halfway, but roughly, and hence these two energies are roughly the same for the two elements. And this ends example 30.9. In example 30.10, we're going to consider an underdamped LRC series circuit. In particular, we're going to calculate what resistance this circuit needs to have so that its frequency of oscillation is 1/2 the undamped frequency. We'll begin by looking at the charge on the capacitor in the circuit as a function of time. And in this diagram, we're going to consider the capacitor to be initially fully charged with no current in the circuit, and then we tie the capacitor in and the circuit begins to oscillate. So basically the charge on the capacitor oscillates like the cosine omega t, but it's confined between the limits of an exponential decay function, so it's confined in the envelope of this exponential decay. And after a few oscillations, it damps out to 0. The frequency of oscillation in this case is given by equation 30.18, where the R is the resistance in the circuit, and that's in fact our target variable. The undamped case corresponds to R equals 0, and that's equivalent to just simply an LC circuit, and its frequency is 1 over the square root of LC. So we're simply going to set omega prime equal to omega over 2, as shown here, and replace the omegas by the respective expressions. And we get this expression, and now I can square both sides and solve for the target variable R. And I find that R is equal to the square root of 3L over C. When R is actually equal to something a little bit bigger, the square root of 4L over C, the circuit becomes critically damped and no longer oscillates. And hence this is a little bit below this, and the circuit is underdamped. This ends example 30.10.